Okay, started, Roger.
All right, great. Welcome everyone. So today we will be doing the last session on binary search, at least for now, third session. So if you are joining in between, I will just like to tell you that in the first part, we went ahead and we covered a couple of commonly found templates. And then in the second part, we continued with the basics where we went ahead with figuring out how to binary search on real numbers. And then we did some problem on binary search the answer, which I'm saying BSTA here. So if you missed that part, I would consider you to go take a look into the SDA skills, and then you can see binary search. This is the first session, and then the second session is also uploaded. So you can go take a look whenever you find time. And then now we'll move ahead and we'll go to the third session. And the agenda is we'll go through maybe a couple of problems. These two problems are basically very similar, first two problems, and they are still very similar to what we already covered previously. So we'll see what we will do there. Then there is another one which was suggested by, I think, Shashank, I guess, this problem. And we will see how we can apply binary search to solve this problem. And then there are some classical problems like longest increasing subsequence, Russian doll envelopes, and then super egg drops. So I'm hoping that we will finish these three soon, and then we will go and cover these problems. So in almost 2 hours or something like that, we will try to cover these many problems today. So anyone has any question before we start? No, so that's great. All right, so let me see if things are working today. Okay, can I draw? Yeah, I can draw, that's good. So generally suppose you are a problem writer. Think from that perspective. How would you create a difficult problem in binary search, which needs binary search? I think normally there could be three parts, right? Maybe there will be something going on here, some logic, like, maybe there will be a DP, or you are evaluating some certain things in this part in the beginning. Then what will happen? You will recognize some pattern on the data, and then you think, okay, hey, I'm working with this thing. It looks like I can apply the binary search idea, which we just talked in last two sessions. So maybe you will have that part here, your core binary search idea. That is where the template we talked about could be applied. And then in that template, I separated it into two parts. One part was moving the pointers. The other part was the okayness. That okayness may depend on the problem statement. And depending on that, your okay, let me call it okay, let it call it BS, core BS. And here could be anything. It could be some DP you may be doing, or you are doing maybe some other, you are traversing an array, you do something, then you sort something, I don't know about it. So these could be three parts. If you are a problem writer, maybe it is also feasible for you to write a problem so that this binary search will result into a certain function. We can have anything here. Here maybe it could be graph, I don't know, or it could be another DP, or it could be another even binary search. You could be even that much creative that even this could be another binary search. It all depends how creative as a problem writer you could be. If I'm thinking I have to write certain problem, I have to make these kind of constraint, and then that is feasible. So when we were doing simple problems, this this was not even there. It was just, you were given some sorted array and you just started here, right? Everything was in this area. And then OK function was a one-liner maybe in the beginning. Then we did couple of BSTA, binary search the answer problem, where again, this thing was not even there. And then we started doing some binary search, and then this one started to get a little bit complex, right? So I'm giving you, this is the overall big picture. I don't know what will happen in today's problem. Probably, I definitely know that in the next problem, OK function will get like first problem is path with maximum minimum value and then path with minimum effort. We'll take a look together into that problem. So let's close this one. So this problem is basically so there are multiple paths from 5 to 6. You start from the first corner, topmost corner to the bottommost corner. And what you have to tell that what is the maximum score in any path, but in that path you have to take the minimum value. So in this path, which is highlighted, the minimum value is 4. If we take this path 5, 1, 7, 4, 6, for example, then in that path, what will be the minimum value is 1, right? But our problem is we want to maximize the minimum in that path. So if you remember in previous session, we talked about couple of places where you can think like, we can use binary search. So it adheres to that, hey, like if I can have a minimum path of 4, for example, in this case, then I can definitely question my criteria that, okay, can I achieve a score of at least 4? That is true. Or at least 3 will also tell me true, right? If 4 is the right answer, and if I ask, can it work for at least 3? So yeah, if 4 was the right answer, so any path with like, that kind of answer will tell you, yes, that will work. But any path which has a score of 5, that will not work. So to find the solution using binary search. So at this point of time, now my question reduces to okay, because now I know this part, true, 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 false, false, false. This is how I can ask the question. And then the remaining part is I'm interested in the max value, right, which we can have here. So because 3 will also tell me, yes, I can, like 3 satisfies that question, 2 satisfies, 1 satisfies, everyone satisfies. But the last guy who satisfies is 4, and then from 5 onwards, it will not satisfy that question. So now the question is, okay, how do I determine that? So now the question is, okay, if somebody tells you, can you test whether we can make a score of 4 or 2 or not? So that now transforms into a graph problem that you start from here and you reach here. Is there a path which can give me a score of 4, for example, or 2 or 1? And that is exactly what we will be doing. So our core, like, logic is something very similar as we used to do in previous session. You might have seen it so many times. Nothing had changed. Now again, the responsibility is assigned to low, and high is the max plus 1. That means high will never be an answer. So that's why I provided invalid value. And then we check this okayness, and this okayness now transforms into a graph problem where I do the usual BFS, where I can go in all 4 directions. I start with the first value, and then I check the criteria. So let me make it a slightly bigger. Yeah, I look into the new X and new Y coordinate. If it is within the range and it is not visited, and this is the constraint, basically, this is the core part of the problem. If this value is greater than equal to mid, then I add it to my possible path. As soon as I reach a destination, the last row, last column, then I can return true. And then this is BF, you guys must be knowing it. And then finally, we return this value, whether it was true or false, right? So the idea is same, just this part changed. And so now, like here, this part is just changing. Not a big thing, but you may see this kind of problem. So, and this problem is exactly same. I will just show you this problem, and I will explain you also. Here the problem is almost same. The thing is, return the minimum effort required to travel from the top left cell to the bottom right cell. And what does effort mean? Is suppose if I'm going from 1 to 5, so 1 to 3 will require me 2 unit of effort. 3 to 5 requires me still 2 unit of effort. 5 to 3 will require me 2 unit of effort. 3 to 5 will require me 5 unit of effort. So in this case, the minimum is 2, right? So output was 2. Suppose my path was 1, 2, 2, 2, 5. So 1 to 2 was 1 unit of effort. 2 to 2 was 0. 2 to 2 was 0. And 2 to 5 was the delta between that is 3. So here you will see there is one effort which has value 3. So I would not prefer that, because in previous case, my maximum effort in a path was just 2. So that is what we are trying to find, right? So it's almost like the similar, previous problem, only the question is different here, right? So how can I tell? So the answer is, if I can achieve minimum effort of this is how I am framing my question, by the way. Can we achieve minimum effort of mid? So can we achieve minimum effort of, say, I don't know, in this problem it's 2, but suppose if I say I can achieve minimum effort of 5. So if I can do something in minimum effort of 5, I must be able to do that in minimum effort of 6, minimum effort of 7, right? Because that's always good, right? It's helping me out to have extra effort as a backup, but I can continue to do that. So the thing is, I have transformed my question into like this way. So true, true, true. And then here, after certain threshold, it will become false or false. And I'm interested to find true. And looking at this problem, I know that most likely I will be interested in high, returning high. So as you can see in the template we talked about, I gave invalid value to low, a valid value to high, and then again similar logic where I will return high. And then again, it's another BFS. The only change is this core logic will be different, where now I am checking what is the delta between the new XY coordinate versus the previous coordinate. What is the next, what is the effort? If it is within the threshold, then I will continue to add it to my possible path. Otherwise, I will ignore that, and that's it. So I covered these two problems together because they were very similar, and this could be complex, easy, very straightforward one-liner. But yeah, nothing special about that. We didn't had enough time, otherwise we could have finished that in the previous session. So with that, we have spent, I think, 15 minutes. We'll go to the next problem. Anyone
There
has any question, by the way?
Yeah, one quick question.
Yeah.
What is the significance of using the binary search, right? And how many, this also we can do without binary search, correct?
Right.
Then why we need to use binary search? What advantage we are getting?
So idea of these sessions are twofold. One is, since we have already planned to have a session of binary search, right?
Mm-hmm.
So there are two ways we can do it. One is we can take one problem and we can talk about different ways to solve that, right? So that could be one problem, and that could be one way to do that. Another is we will try to see how can we apply a certain technique we are trying to utilize, and that is what we are aiming here. And
Okay.
yeah, and on the second part, if you have problem, like why, like what was the intuition behind it, that should be cleared with the way we are approaching this problem. So think about it, how I think in general, and you may agree or disagree, but when we talk about binary search, how many of you may be familiar with like lawn tennis, right? So here it is. Suppose I am asking you to work on your forehand, okay? And I am a right-handed player. Now the ball comes here. Normally, you try to be in center so that you can hit ball from all the places. So of course it is natural for you to go and hit the ball, right? Here, if there is a ball here and you have a very nice backhand, you will just come here and apply a backhand, and ball will go wherever you want. But what we are trying to do in certain cases, we will run around here and then we come here and we'll try to put the ball maybe here. Maybe we will try to put ball there. And the purpose and where it could be useful is maybe in certain situations, you may require this. If your opponent is not able to handle, say, a heavy top spin, which you can't generate with your backhand, you will try to do that, right? Your footwork will get better. Exactly the way we are trying to do it, we'll figure out the different ways, different scenarios. Maybe in this problem, you can apply certain ideas, but maybe in certain problem, you may not be able to apply that idea. Maybe in that case, binary search will help you. Does that give you like
Yeah,
why?
that makes sense.
Yeah. Okay. So that's why we are trying to do it. So with this, we are done with this problem. These two problems are now, nothing is left over there. So we'll go to this problem. This is an interesting problem. So where was the problem? So given an integer array, remove a subarray, can be empty from array such that the remaining elements in array are non-decreasing. Okay. And return the length of the shortest array. So let me write an example. So 1, 2, 3, 10, 4, 2, 3, 5. Okay. So you are given an array 1, 2, 3, 10, 4, 2, and what was the last one? 3, 5. So you have to remove certain part of the array so that uh, the remaining part becomes a sorted array. So what should be the answer, guys, here?
1, 2, 3, 3, 5, I think.
Right, 1, 2, 3, 3, 5 will be the remaining. So most likely you will cut this part, right? So if you cut this much, then we have a sorted array. So that is the problem. And as you said, I couldn't saw your name, so sorry about that. previously. I think there is a better way, even like, time wise. Most likely there is a 2-pointer approach, which I haven't seen yet, but I think that is preferred. But we will still do it using binary search, and we will see why binary search, what was the idea behind binary search, how can I even think why, how it can actually come to the picture. So let's see. Right, if I remove n-1 element, it will definitely work, because any one element array is a sorted array, right? And if everything is already sorted, then I don't have to do anything. That could be the best case, right? We will look at a general case. Suppose we don't know about it, what is the ideal part, but suppose you don't know about it. Suppose there has to be a solution. Suppose this is the part where the solution lies. So let's call it, here is the ideal cut. Okay. So what does that mean to this part and this part? At least it means a couple of things. One is, let's call this left part, and let's call this guy right. And let's say the length is n. So one thing is definitely left plus cut plus right. This has to be equal to n, right? If n was the size of the array. So basically cutting something means we just ignore that value, these guys. So if we can ignore these values, and this left part is ascending and right part is also ascending, we have a chance that the remaining part, so left and right, if we combine those guys, they can become a sorted array, right? So now, is that always true? If I write the numbers like this, 10, 4, 2. Okay, actually, let me write one here. If it was like this, and I cut this much, then still that will not give me the right answer, because even though this is an increasing part and this is an increasing part, these values are not the way they should be, right? Any value greater than 3, any value greater than this guy should be here, because I know everything after that value is sorted towards right, so it should be okay. So we will have to also be very, we should have a keen eye on what this value is and what this value is, other than cutting this, trying different cuts. That is one observation. And let me write the relation also for that. So let's call this guy 3 in this case, like this particular 3. Let me tell this value is val left of cut. What relation we need to have? That this value should be less than equal to val right of cut. That is necessary. That is one observation. So second observation is, okay, how can binary search work? Like, why binary search? So again, if I tell you that, hey, suppose X was the right size. So in this case, you can think, instead of X, I say 3 is the right size. 3 is the answer for this problem. So if 3 is the right answer of the problem, can I say if I cut a value of 4, I can still have the array sorted? That is a question for you guys.
Can you repeat this, Khalil?
So the question is, suppose 3 is the right answer, which was the case here. Can I also say that if I cut 4, like, 4 size instead of like 3 size subarray, 4 size subarray, I can also possibly get the right answer.
Yeah.
Right.
Yeah.
Cool. So if you can see that relationship, that after a certain threshold, if I continue to go up, and of course the size should be like, valid. Of course, you can't go index out of bound, just forget about that case. But if that is feasible, then of course, we are seeing this monotonicity behavior here. Like there will be couple of false. No, if you cut just one value, it's not enough. If you cut just 2 value, not enough. 3 maybe not enough. 4 maybe not enough. But maybe after certain threshold, you will start to get these true. Right? And we have to find this value, the first true. If I, ask the question like that. So once you are given a certain answer, can we simulate whether it is possible to figure that out? Hey, is it a right answer or not? Is 3 a right answer or not? If somebody tells me, then I can apply a brute force, right? I can try to first cut this guy 1, 2, 3. Then I can try to cut 2, 3, 10. Then I can try to cut 3, 10, 4, and try to cut 10, 4, 2. And maybe here I should be able to figure out the answer. Otherwise, I will try to cut next 3 elements, something like that. So that is the core, thinking process behind the solution. Now, of course, you need a couple of values here. So when I am working on this part, there are 3 parts, right? 3 parts. So here is the cut part. So I need this information. Of course, I can easily get this information with what is the value here and here, because I already have an array and I know the index, then I can figure out easily. But also to get this part, whether the left plus cut plus right is equal to n or not, I may try to have the size here. What is the increasing and decreasing size? I don't know, unless I can also get this value directly from index. You have to test whether this is actually increasing and this is also actually increasing or not. That is now another problem which we have. That, okay, I will do that part. That's not a problem. I can try to do this simulation. But how to quickly check whether this part is increasing, this part is increasing or not? Maybe this part was increasing till some place and then it dropped and then it again start to increase, right? So how to quickly do that? Similarly, on right side also, maybe it was again similarly growing up. So you have to also handle that information. One way is, of course, you can brute force, you can do a loop and you try to find it out. Another one is the idea of the prefix sum, where you can actually continue to, you can just do this one scan in the beginning itself. So at each index, you can store that information in some prefix array, and the same information at suffix array. And what they can store is like how many, like is this guy can store how many numbers towards my left are less than equal to me. And the same guy, the suffix array, this can store how many guys towards my right are greater than equal to me. Then when we will be scanning, right, we will go here, we'll go here, we'll go here. I have all the information at my fingertips to actually go and do the simulation, right? So at least is the idea clear, guys? And then once you will look at the code, I will explain more. But are you clear about the intuition and then why having this will help? Prefix and suffix. Okay, no means probably yes.
Yeah, to some extent, yeah.
Yeah. Of course, up to some extent, it's fine. I will show the code and then maybe it will be more evident like how it is happening.
Yeah.
But why part should be fully clear before we look at the code? Is the why part clear? Like forget the how part. I don't care about how part yet.
Yeah.
So why is clear, right?
Mm-hmm.
Because the intuition is if 3 was the right answer, then 4 will definitely be the right answer. Then 5 also will be the right answer because I can, cut this part, the actual part, and then I can cut the neighbors also, right?
Yeah, that is correct.
Yeah. So the intuition is there. And then let's just look at the code then, and then it will be clear. So this is what I'm doing. Like, you go to the array length, and is array length. We fill this everything with 1 because every index at least is less than equal to itself or greater than equal to itself. So this is what we are like, having to begin with. Then we look at the neighbors towards left for each element. And then these prefix tells like how many numbers towards my left are less than equal to me. So if I is greater than prefix I minus 1, then it can increase its counter. We do the same thing from right side, right? So after this, what we will have, if I ask question to any index, it will exactly know how many guys towards its left using this. We have that information available. Okay. Now, as we just said, like, our problem is built up like this: false, 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 true, 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 things like that. So now, what should I return? Low or high? Can you guys tell me? This is a template question.
Can you scroll up
Yeah, sure.
in the code?
So the question is this one. If I have built my question like this, which will return me false, 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 true, 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 and I'm interested in the true, this value, would I be returning low or high?
High, I think.
Yeah. So that was again discussed a lot. So I hope this is now mechanical. So that is what we are returning here. Okay. So we'll go to the core logic soon, but what that means that I will assign invalid value to low, which is -1, and to high the max value, which was possible in this case. And then we do our usual template. This OK requires more things actually to figure things out. So we pass all the parameters, prefix, suffix, mid, array, and then we finally return high. And then this was the core logic which we just discussed. So let's look into it. So left was, okay, so start is basically, we are starting with some place, right? So start was, I will start here, for example, with the 1 value 1. And then my window will be 1, 2, 3, for example, if it was and then the next will be 3, 10, 4. And that is what we are simulating. So we start with this value. So I know where the window will end, start plus cut size minus 1. And then the left part will tell me, okay, how many numbers towards my left are uh, smaller than equal to me. So that is where this prefix calculation come handy. And this is just like, bound check. So just, ignore that. It's easier to understand if you just look at it. And similarly for the right part, how many numbers towards my right are greater than equal to me. So suffix will tell me that. That is why we created those two values. Okay. So now you remember value of left and value of right of cut is this case. This case where we derived. Suppose the example was this one. Let me put from a different color. Suppose the example was this one. So even though this guy is increasing and this guy is increasing and has this right size, prefix and suffix, still this value is not smaller than equal to this value. So even if you try to combine them and if you try to get rid of all this value, eventually you will not get the right sorted array, right? So that is why we thought, okay, we'll also check these values, and these values were value left of cut and value right of cut. Okay, so that's what we are getting. Whatever was my start minus 1, that would be my value left of cut. So that is array start minus 1, right? Because the rest of the thing is basically just a bound check. Similarly, value right of cut is end plus 1, array end plus 1. Now we try to see whether we match both the criterias. The two criterias we had defined was that, hey, left plus cut plus size, if this equals to n, then ignoring the cut part is sufficient. That was first criteria. And the second criteria was to handle the case we just talked about, that value left of cut should be less than equal to value right of cut. And that's it. Should be, if these two work, then we can return true. If not, then we will return false. So that is binary search solution for this particular problem. And it was really slow, I guess. When I submitted, it was slow. But so probably I would advise you to go and look into this problem and then check the best solution. But here we are just demonstrating how this logic could be complex, as we talked in the beginning, this part. As you can see, this okay part now requires, more data, more things to analyze. A certain, simulation requires more, to calculate things. So that was this particular problem, guys. After this, I think we have finished 45 minutes, so we are good to go with these classical problems, and we'll spend some time there. But anyone has any question on anything so far? Okay. No questions. Normally means either good or totally gone case. So hopefully it's good.
Yeah, I think it is good. Yeah.
Okay, okay, nice. This is a very famous problem, longest increasing subsequence, right? And are we going to cover that in next session also? I think in DP session, probably this is one of the problem, I believe.
Yeah, I think it is.
Okay.
Yeah, but we can. Yeah, maybe there will be different approaches, right? The Dpe approach.
Yeah, totally, totally.
Right.
I
can
will
cover
still
that
cover.
also.
I will still cover it. I was
Yeah,
just
no problem.
joking.
No issues. Yeah.
Okay, so longest increasing subsequence. So let me try to explain the problem. I am pretty sure you guys already know this problem. So still, I will take this example and explain what does that mean and how it will work. Okay, let me make some space. What's in the chat, by the way? Thank you. So okay, so the example was 10925. Okay, 10925. Oh, red is not good. Let me change the color. Ten, 9, 2, 5. And what else?
37101 18.
Thank you very much. 37101 and 18. So we have to tell what is the longest increasing sequence size in this particular case. So longest increasing subsequence. So there is a difference between subarray and subsequence. If when we talk about subarray, they have to be adjacent. In subsequence, you can ignore that part. They don't have to be adjacent. So for example, in this particular case, the answer is, for example, 4. And how 4? 2, 3, I think 7, 101. That could be the answer. 2, 3, 7, 18. So all you have to return is 4. See, because 2 was here, then 3 was here, and 7 was here, and then 104, 101 is here. So we ignored 5 here. You can see we ignored 5, because if I take 5, then actually I have to make 2, 5, 7. Actually, that would have also worked in this case, or not. 2, 5, 7, yeah, actually.
Yeah, it should.
Yeah, 2, 5, 7, 101 could be another way to make it. But the thing is, we don't have to tell these things, like how you build this. And I haven't actually solved that problem myself, at least for today's session. We are interested in this number. Like, what is the longest increasing subsequence if you are given a number? So what approaches you guys have come across? And we will talk about, I think, I will talk about first the Dpe approach quickly, and then we will go to the binary search approach. So Dpe approach, let's talk about it. It's commonly asked question, and I'm pretty sure most of you may know. So at any instant of time, what is important for us? So one thing is definitely, if you are given a certain array, which was given here, by default, everybody can have at least one value, because any sequence can start with itself and end with itself, right? So that is not a problem. Other than if I am at here, or suppose this is the ith index, and I want to find what is the longest subsequence ending at me, right? Which includes me. So let me write the definition. Definition, I can write something like length of LIS ending at me, including me. So now the restriction is that I have to be included here. Okay. So for example, if we were trying to do this thing, and in this previous example, let me try to take some value. If I was trying to run this value, and suppose I was standing at 2, I was 2. So rest of the values were towards my left, 10 and 9. Will I try to include those guys or not? If I include 10 towards my left, can I come towards right? Probably not, right? Because including 10 makes no sense. 10 2 will not give a LIS. Similarly, 9 2 is not a valid solution because 9 will not help 2 out. So 2 can stand by itself. It checked everyone towards its left, and it checked, hey, where can I stand so that I can increase the LIS length? So that was not clear. So let's check another example. Let's
Sorry,
check.
I may have missed it. Why did you pick 2?
So 2 is I basically here.
Okay. So why 2 then?
Why did I choose 2 as an example?
Right, yeah.
Just to demonstrate something. So for now, I just
So you can pick any number then, right?
Exactly. I will pick other numbers now also, but we started with 2.
Okay, got it. Okay, thank you.
Yeah, no problem. So now suppose I pick randomly maybe 7, for example. And guys, here I means index, but think about its value, for example. I'm looking at 7. So 7 may ask a question to its neighbors towards left. Hey, I have a LIS of 1 because everybody has a LIS of 1 by default. But can I stand towards right of one of you guys so that we together can make a bigger LIS? So he looks at 10 and no, I am not bigger than 10. So forget about it. 9, same thing, like, 7 is not bigger than 9. So he can just ignore. 2 and 7. Yeah, having 2 and 7 will help 7 because then 7 can at least update its number to 2, right? It had just 1 length LIS, now it's better. What about 5? So by the way, if we haven't drawn that, we should go step by step, then it will be clear. So let me first actually do I equal to 5 because you won't understand that 5 already updated its value. So 5 was doing the same thing, what 7 I was trying to demonstrate with. So 10 didn't work out for 5, 9 didn't work out for it, but 2 did work out. So 5 will say, hey, my LIS is 2. That's great. Then we work with 3. So for 3 again, 10 didn't work out for 3, 9 didn't work out for 3, but 2 did work out for 3. So 3 will also tell, okay, I also have a now LIS of 2. So now when we go to 7, so now let's go to 7. So again, we are doing the same thing. 10 didn't work out, 9 didn't work out, 2 worked out. So 7 will update for now value 2 unless it finds something better. Then it looks at 5 now. 5, it can include because 7 is greater than 5. So now 257 is a better value. So now it will say, okay, what value you have? So 5 will tell, okay, I have value 2. So let me just update +1 because I can stand just, right of you because it find a better candidate. Now it looks at 3. Then 3 tells, okay, I can give you 2. Then it's upon 7, and it depends on implementation, how you want to do. You can say, hey, am I getting a better number? If I'm not getting a better number, then I would either ignore, or I can even take 3. I don't care. But the story is this length will be 3 at this point of time. So what we are doing at every instant of time, if I'm working here, I'm looking here, right? So all the values of j which are less than I, I'm looking into that, and then I'm updating our DPI. So, like, something like this, we can write that DPI is equal to 1 plus max DPJ where j is less than I. And also when it will do, it can do just, we just run it. You have to also check that num at I is actually greater than num at j. Then only we can do that. So this is a well-known problem. And what time complexity do you guys think it will have?
N square, I think.
Of n square, right? Because yeah, here suppose this guy will look at how many n minus 1 neighbors towards left, then this guy will n minus 2 plus n minus 3 plus and so on. So eventually it will be O of n square. So now the question is, and this is a well-known problem, can we make it better? So answer is of course yes, because somebody thought about it, and I'm just trying to use his intelligence. But let's see. Anyone has any question on this part, DP part, by the way, guys? Okay, so no questions means good. Okay, let me try to make a space here. I want to have the same example. Okay, so now look at it in a different way. So 1092, right? That was the number. 2, was it 537, I guess? 537, what was the last two number? 101 and 18, okay. Okay, now look at it in a different way. So suppose we start with 10, okay. 10 comes, 10 starts the thing, okay. So we'll talk about it. So at this point of time, suppose 10 come here, it can tell that I have a one size LIS, and that is fine, right? Nobody has any problem with that, right? Now 9 comes. So the question is, I don't know what is in future currently, but would you like to have, because 9 can also tell, hey, I can make a one size LIS beginning with me, because 10 was greater than me, so I cannot work with him, but I can start my own LIS. And if you take me, then I also give you one length LIS. So what would you prefer? Would you try to have 10 or 9 as your representative here?
9.
I would prefer 9 because that gives me an option to increase my length by 1 if I have 10 in the future.
Exactly. So very nice observation. So because in future, again, you could have like, instead of 2, you could have 10 here. Had you taken 10 and then you again get 10, then you will continue to remain as a one length sub, sub LIS. But if you take 9, it can work with everything which 10 could have worked with, and also everything which is between 9 and 10. That will also work. So that is why if something smaller comes up and gives you the exact same length, it is preferable to use the smaller one. Is that concept clear? Because that is the core part of this like logic, by the way. We will do more examples, so let's do that, no problem. And then things will become even clearer. So now 2 comes. So now if 2 comes, then we'll have 2, because see, now 2 comes, then I can start something with with myself, and I can still give you one length LIS. So by the same logic, we are saying, yes, let's prefer 2. Then 5 comes. 5 is telling you, hey, actually I can work with 2 and I can give you 2 length LIS, right? So at this point of time, if suppose nothing was in future, I can tell my answer is at least 2. Sounds good? Hope so. Now 3 comes. 3 can say, though I cannot work with 10, 9, 5, but I can work with 2 to give you equal length LIS, like means 2 length LIS. Would you prefer to have me? Again, the question is, would you prefer to have 3 as representative or 5 as the representative? That's the question we have. Answer, guys. I know some of you already know, but I would not know unless someone tells me. That's clear.
At 3, we used.
We will use 3.
Yeah, 3 as the representative, right?
Yes. Yeah, because suppose 4 comes, then 5 was not a good choice, right? Because 4 could come in future, and having 3 will give me a better answer in future. So we are done till 3. Now 7 comes. 7 will tell me the same thing, that, hey, I can work with 3 to give you a better length LIS, which is maybe 7. That is fine. Okay. Same logic. 101 comes. He can tell I can work with 7 to give you a 4 length LIS. Okay. 18 comes. 18 tells I can't work with 101, but I can work with 7 to give you still a 4 length LIS. Okay. So with this, we know that this is the answer, right? And now let's look at, if the idea was clear, that whom they were looking at. So we started with 10. So 9 was looking at, is there anyone towards my left with whom I can work with to make a bigger size LIS, right? It couldn't find anyone. 2 couldn't find anyone. But what happened to 5? 5 was looking into these guys. But is it required for him to look at these guys sequentially, or can he do a better search? That, keep your idea, mind on that. We'll go through a couple more examples. 3 is now also asking the same problem. Hey, I have to find something which is smaller than me towards my left, but do I have to go and check all these guys with whom I can work, or can you provide me something better? 7 has the same question. 101 has the same question. 18 has the same question. So the only way, because you remember in previous case also we were doing the same thing. We were going through all these guys as J was going to different values towards every value towards left, and it was trying to find it. So yeah, so here, can we expedite that process? And when we were containerizing things, did you guys see that we are building an increasing length array? See, this array we are building is monotonically increasing because I'm building a representative here, right? Now, if there is a bigger guy, then only it can work with this small guy to make a bigger length value. So that is the idea of this approach. If you can build these representatives, they are in an increasing order. And so when the new guy comes, it can find its insertion point, ideal insertion point in this sequence. All it has to look at, suppose like if there was another, like 20 came here. So it will look at this value 2, 3, 7, 18. Hey, where do I fit? Okay, so 20 fits here. Okay, then it also means that I can give you a better length. Here you had just 4 length LIS, I can give you 5 length LIS. Suppose now 4 comes, for example. Okay, so now when 4 comes, where does 4 fits? 4 will fit somewhere here, right? When you binary search the index, where should 4 fit? So we will just remove 7 and we can have 4 here. And that is how we will continue moving forward. Is the idea clear, guys?
Can you tell me once more, how is the longest sequence? The graph that you mentioned.
In the graph, so you are talking in this case. Sorry, can you can ask?
Yeah, I didn't understand how. I got the binary search part, but I was wondering how did you fill those values like 2, 3, 7, 18, and 20?
Oh, okay. So in the beginning, we started with 10. Okay. So 10, there was nothing at that point of time. So we filled 10 here. So let me use another color because we already have the value filled in here. We started everything here. So we put 10 here and 10 tells me, okay, we have 1 length LIS. Then 9 comes. 9 cannot work with 10 to give anything better. So 9 will replace 10, okay? And it can still give the same length LIS, right? That was the question, like, would you prefer 10 or 9? And then we agreed that 9 is always better because it's smaller. In future, we can have 10, then it can help us with that situation. So with the same idea, 2 came, and then 2 even replaced 9 because 2 was smaller than both these guys. So at the end of all these operations, this guy only had, this container, if you say, only had 2 value here.
Okay.
Okay.
Can you go forward with 2 more values, please?
Yeah, sure. So 2 is done, right?
Yeah.
So now 5 comes. So now 5 comes, then 5 says that I can work with 2 to give you a better length. So 5 comes here and it tells, okay, we have a 2 length LIS going on here. Then 3 comes Then 3 will tell, okay, I also can work with 2 to give you 2 length LIS, and 5 was already sitting there, but with the same logic, it is preferable to have 3 rather than 5, right? So at this point of time, we have 3 here. We don't know in future what will happen, but so far, like this is how it is going on. Then 7 comes. 7 comes and it tells that I can actually directly work with 3 to give you a better length, which is 3 length LIS. So I said, okay, we will create a new container and we have a better answer. So 7 comes here.
Okay, I see. I see. Point. Okay. Each index is actually the length of the longest increasing
Right.
at that bucket. Okay.
Right. So what is helping us here? See, the thing we are creating is C is increasing, right? So the earlier in the Dpe approach, we had to go back and we had to check all the values, right, towards left. But the way we are doing it, now when 7 comes, 7 asks, because it knows that these values in this bucket are already sorted. It just asks, what is the right insertion point for me? And whatever is the right insertion point for him, we can tell what inserted even after 18. So we will get a 5 length LIS, right?
Yeah.
Right here. But suppose we had just 4, then 4 will be inserted somewhere here. But we will still have 4 because who knows, maybe in future we have something better. So maybe having 4 can give us a better answer in future. That's why we left it there. Right? Because maybe you can have, I don't know, maybe 5, 6, 7, 8, 9. So if 4 stands there, then, we can have 5 here, 6 here, 7 here, and we can continue to generate a bigger LIS, right? So that's the core idea of this approach. Is it clear, guys?
Yes, Roger.
Yes.
Awesome. So if it is clear, then we'll just look at the code. Now code will be very evident. So I have explained the same thing in the comment, and I'm pretty sure you guys may already be in the previous class, but if you were not, then all these codes, at least for now, they are available here. And the link is already shared in the Discord. So you can just ask me for the access and I can give you, which have all the codes for all the problems we have done so far. I will probably do more questions in future as new problems come. So I will add it here in this document itself. So it can be, in theory, ever-growing list. That's the idea I have. All right. So we do the exactly same thing. We create an LIS array. We just search. You remember when 7 came, it was searching, hey, what is the best place for me to be inserted? Okay, so suppose this search gives it that value, then at that place, we insert this value, 7. And we see that, hey, it is telling me that it's the max value. That means what happened in the 20 case. In the case of 20, it is telling me, okay, whatever index you have, you should be inserted after that. So, okay, let's create a new max value, because now we have extended our existing LIS and we'll just return a max here. So this is our binary search part. And that will be exactly like we write any binary search. So this is a sorted array. There is a target and we are asking, where does this guy fit? Okay. Actually, sorry, here is the target and here is the high, current high, and where the target fits. And we do the common, binary search. The question I'm asking is the current number greater than equal to target. So I can find the right index to put that value. So that's it. Nothing nothing very complex. And once you write that, this is a very simple code, right? And that gives you n log n solution. So that is LIS in n log n. I know there are other approaches, but I haven't coded it yet. This is like where you can use data structure, even binary search tree or things like that to also solve this problem in n log n time. So there are multiple ways to solve this LIS. It's a very classic problem, that's why. So that's it for LIS. Any
Yeah,
questions?
Roger, can you move to your OneNote screen where you were doing the example? So when in this example 2, 3, 7, 18, and 20. So when you insert a 5, do you make space for it, or do you replace 7 by 5?
So I replace 7 by 5 because I don't care about building the actual sequence.
Right. You already have the length covered for the
Yeah.
previous one.
Yeah, but if you have to, that's why in the beginning I told you I haven't written code for that. But if you have to also care about that, then you will have to do more bookkeeping, and then maybe you have to alter a little bit, but it's possible, doable. So yeah, but I'm overwriting. So at any point of time, you have just single value at any index.
Right.
Okay.
So for the input example, Roger, can you go over, like, let's say the input gonna have 0 and 1 after 20?
After 20?
Yeah, have a 0 and 1.
Okay. Okay, so you are saying we have 0 and what?
1.
Okay.
Yeah.
So now what should happen? Suppose 0 comes, right? And let's see, this was prepared so far, right?
Right.
So 0 comes. So the idea is length LIS, because this container is for one length LIS. 1 comes, then one can replace, because one will search what is the right place for it, and it will tell, okay, this is the right place for you. So one can just replace 3. And why it is able to replace? Because anything towards left does not mean anything. However, if you look at, if you are, and that is why I in the beginning told you, it is not giving you the right LIS. If somebody tells me, hey, you replaced it, so is the LIS 0, 1, 4, 5, 6, 7? No, it's not. But I am able to do that because I only care about the count. You get the point?
Yeah. So the LIS is the same. The length, the length of this LIS is still the same. We only change the value. So, in the future, if we have any
right
better value, we might have better longer,
right.
Longer sequence.
Longer sequence in future. If you have to calculate, then ideally you may have it you can have instead of just one value, a list or something with more bookkeeping, and then you have all the representatives, and then you can build out, okay, maybe you have multiple solution in this case, like right, 100, 118 was the right answer, and maybe 100 will know like what was the previous value, and did it come before or after, and things like that. But so I will just ignore that part. But theoretically, it's more bookkeeping, and it should be doable.
Yeah.
Okay, so the intuition is clear, implementation is clear, right? Everything about LIS, both the approaches. Okay, I hope so.
Yes, yes.
Cool. Excellent. So now for Russian doll envelope, why don't you guys read it? I mean, read this problem, because I will take 1 minute break, drink water or something. And then I will try to explain the problem. It's a very important problem. Has anyone solved this problem, by the way, earlier?
Yeah, I don't remember exactly, but similar problem. The box stacking one is a bit similar, I think.
Oh, nice. So this problem is, okay, let me try to draw it here. Sorry. So Russian doll envelope. So idea is, I don't remember the exact numbers, but let me explain the question idea wise. So you have been given certain dolls and you can put, one inside other, something like that. That's the idea. And you have to tell what is the maximum number of dolls you can, Russian doll. That's what the problem is saying. So you will be given width and height, of course. So suppose this is width, this is height. Again, no matter what color I choose, it doesn't matter. Okay. So guys, we are stuck with red pen. Otherwise, I don't know. Maybe I clicked something. But okay, we'll try with red pen. So width and height. So if you can put the stuff inside this only if the width of this guy, second guy, is smaller than width of this guy. Also height should be strictly smaller. Okay. So how would we do that? That is the problem. So even before that, let me tell you, if you are given different length sticks, for example, like many sticks, and you want to find what is the maximum number of, so the idea is you can put one stick over the other stick if the stick size is smaller. So this is a smaller stick, so you can put this stick here. And let me make it a slightly bigger if maybe this is also big, but suppose there's a really small stick, you can put, so once the second, so let's call it A, B, C, D, E, F. So on top of C, suppose I placed B already. Now, if I want, I can put F here. That's how the problem is. What would you do that? How can you do that? Like,
So it's also similar to that meeting room kind of thing, right? In some ways.
In meeting room, you had an interval, right? In that interval, the time was fixed. But here the flexibility they are giving that you can arrange your sticks in any order. Even though I give you like A, B, C, D, E, F, but you are allowed to, mingle it in whatever way you can. And you have to just tell me what would be the answer. Maximum number of sticks you can put on top of each other.
It is the same as the longest increasing subsequence, right? Same as the previous one, where the length is the length of the stick is the value.
So there is no length in this stick problem. That would come in this problem, the actual problem, Russian doll problem. But I'm just telling you a stick which has just width. There is no height.
So for placing F above B, the width of F has to be shorter than the width of B, right?
Did I? What's going on? Everything is so unresponsive. I have no idea. Can you guys hear me?
Yes.
Yeah.
Okay, can we pause the recording for some time? Let me try to figure this out. I don't know, I can't even go to any page at this point of.
Okay, started.
Okay, is my screen visible or?
It is visible.
Okay, great. So yeah, guys, so the problem I was asking in this particular case that, hey, this could be in any order. And all you have to, create something like this. What is the maximum number of sticks which could be put on top of each other? So, I mean, the easy way is you can just sort it, right? Because now order doesn't matter. Longest increasing subsequence, if you remember, the order was, was very important, because in previous example, I could not put 10 right of 9. But here in this problem, I can just sort all the sticks and then I can check the adjacent sticks and see, like, if suppose in this case, A was smaller than B, then I can put A on top of B. And then if B is also smaller than C, I can put B on top of C. So now C can have both B and A. And D has to be, if it was sorted like that, then D has to be either equal to C or greater than C. So it's very easy problem then, right? You just do one scan after sorting and you can figure out the answer. Is that clear?
Yep.
Okay. So now the problem is this current problem. Current problem has 2 dimensions, width and height. So you can have things like this. So you have width, you have height, width and height, width and height. And so now the problem is, how would you pack maximum dolls inside each other? So that is your problem. So now if one other, there are 2 dolls, suppose one doll's width is smaller than, so let's call it WA, is smaller than WB, but if height of A is greater than or even equal to height of B, we cannot, Russian doll them basically. We cannot put one inside the other. So
So you sort it on the width, but in the reverse order. And basically, which means you have the largest width in the first on the first place, and then you compare with all the others, and wherever you have width less and the height also less, I think that should it'll be an n square, I guess. I don't know if it is 1 of n square, but
Sure.
at least brute force you can find the answer, I guess.
Right. We will look into the implementation later. But yeah, the idea is because somehow we have to figure the order, right? Somehow I have to figure the order. And the only way to order is I can sort it. So that is also clear. But my problem is I can't sort on the instant I sort on width, now height I cannot sort, right? Because then sorting was just giving me one way to arrange the items, right? I could have arranged items in a way depending on how I sorted. But if I again try to sort, right?
Hello?
So here we did see that sorting helped to solve me a problem. But here, if I just sort, that wouldn't be enough. However, I could sort by one dimension. So that at least helps me, hey, when you are looking at all these candidates, you don't have to worry about their width. For example, I sorted on width, for example. I can easily tell that width of this guy has to be greater than or equal to width of this guy. Same with this, everything towards right has a more width. So now my only problem is to fit this thing. Can I look at height of all these guys and figure out what is the best I can achieve? Right? There could be many things. What is the best I can achieve? And I'm not looking into height at this point of time. I'm not looking at height because, sorry, I'm not looking at width. Width is immaterial after it is sorted. So I'm looking at one dimension. Okay, suppose this height was 2. Suppose this height was 3. Suppose this was 4. Suppose this was 4. Suppose this was 5. Suppose it was 1. Suppose this was, again, I don't know, 2, 10, I don't know what. We could have things like this way. So now, what does my problem reduce to? That I have just 1D to worry about, but now I have this constraint that I cannot move it. So you remember, now these guys are fixed. It is fixed now that I cannot sort again. So now I have to find out how many maximum, suppose there is an answer 4. I'm seeing 5, but suppose this was the answer. So what can we tell about looking at this? What is going on here? How can I find that?
Maybe we can apply LIS for the height parameter.
Exactly. And this is what is happening actually. Even if you think about it, what I have to do now somehow, when I go to left to right and I'm selecting my candidates, they have to be in increasing order. Then only I can fit them in, right? Because this guy, even though this guy's width was bigger than width of 5, its height is too small. So we cannot fit, this 5, whatever was the size in this box, right? So eventually what we are saying, what is the LIS when you scan from left to right? Is that clear, guys?
Yes.
Yes.
Exactly, that is what we were doing in the first problem. In first problem, we could not sort this thing because you were given a fixed array and you were asked what is the LIS for this thing. Now, in Russian doll, we had 2 dimensions. And we learned using that stick example that if there is no restriction, if I sort it, it's very easy. Trivially, I can go scan the left, like, two neighbors, and I can put one over the other if it is possible, otherwise continue going forward. When it came to 2D, the problem is now width is giving me some idea, but still that is not enough because I have to work on height part. And now we are only looking at one value for each box. And then I can, somehow arrange it so that a small, large guy, I don't have to worry about width because it was already taken care by sorting. So it's just going and checking whether the right guy has bigger length than bigger height than the left guy. So yeah, now it got transformed into your LIS problem after that sorting, and then you can solve it. However, there is something which you have to be careful. So idea is fine, it's not a problem. I don't know whether I can write the example at this point of time. What was the example? The tuple was 54646723. Okay, let me remember 54646723. So, okay, 54646723. All right. So if we sort by one dimension, so 2, 5, 6, so maybe 2. So you will have this thing 2, 3 will come first, then 5, 4 will come, then 6, 4 will come, and then maybe 6, 7 comes. Suppose this is how I did it. So now we know that we don't have to worry about this part. Okay, suppose if we don't have to worry about, then I will tell, hey, the answer should be 3, 4, 4, 7. And say, hey, the definition of LIS is it has to be absolutely increasing. So answer is 3. That could be one way to tell it, but there is a flaw here. Suppose this was not 6, 4, example was 6, 5. So what we will tell 3, 4, 5, 7, which looks like in increasing order, right? So answer should be 4, right?
But we do have 2 6s, like the width is
Exactly.
same.
Exactly. So we have to be careful that I could not totally ignore this value because 6, 4, 6, 5. Here width could be equal, right? In the input. So when we are looking into these values, like 6, 4 and 6, 7, so where was that? Yeah, these two values, I cannot put one inside the other, right? So one way could be do extra check whenever that case is, also like, pass the width and look into it. And the other way is, what if you sort in the reverse order when the things are equal? So what does that mean? If your widths are equal, then it is fine. But if width are not equal, then it is fine because you will not have any problem. But when widths are same, so in this case, 2, 3 had no issue. Okay. And then the next guy was 5, 4. It had no issue. Now 6, 7, 6, 4. What if we sort like this 6, 7 and 6, 4, and then ignore? Then what will happen? You will have 3, 4, 7, 4. Suppose even if it was 5, as I changed the input myself, suppose it was 3, 4, 7, 5. What would be the LIS?
3.
LIS will be 3. Why? Because when I sort from, like, in the reverse direction, when things are equal, that handles that case for me by default, because I could only select one of the candidate. If there are 10 values having the same width, I know I can only put my previous things in one of those boxes. And what is the best value to put that box could be maybe the smallest one, right? So that is the reason I would try to sort in that particular order. When width is equal, then reverse sort on height. And that will help me with a couple of checks, but you could have written the code without even thinking about it. So yeah, is the approach clear, guys? Are there any questions?
Can there be a case like if we sort by width and then do LIS will be different than if we sort by height and then do LIS?
Oh, you are saying, no, you can do in any order. Just one will be sufficient, by the way. You can sort by height and then do LIS on width, or you sort by width and do LIS on height. That should give you the same answer, but you don't need to do both. So I will show you the code, but I think Harshit mentioned another question, so I will briefly. In 2D, what if we had boxes? Boxes means like you can have things like this. You may be given a lot of boxes. And I don't know the question, but the question could be, you are given now 3 dimensions, width, height, and what is that? Depth, something like that, many of these boxes. And your eventual goal is you can build, put boxes on top of each other. Again, there could be similar kind of rule that, you can put one box on the top of other box only if these dimensions are within the range, like width and height. And maybe you have to find the maximum number of boxes which you can stack, right? So in that question, I will just leave it that what you could do, that you can maybe find the area of these boxes, and then maybe they will tell you whether a rotation is allowed or not, because if there is a rotation allowed, then you have to try all the possible combinations of rotations. But suppose if that is not allowed for simplicity, then again, you will have the same problem. Okay, you have these areas, and now you have to find what you can put on top of each other, and try to find this problem and try to do it after the session and see if it makes sense. But that was another application to LIS in 3D. I haven't done it, so I cannot do it now, and we have other things to cover. But at least with that, we looked at LIS basic idea. Then we did the stick problem to just understand that just sorting was sufficient. Form to LIS, and then the same thing can happen in 3D, where you are actually now handling 2 dimensions yourself and let the 3rd dimension evaluated by LIS basically. So that's a food for thought. I will just show you the code, by the way. So should be pretty clear what we were doing in this problem. So the max envelope. So as you guys saw, this is sorting. So first, this means that we are doing in increasing order of width here. Okay. And then decreasing order of height. Only if it is equal. If it is equal, then height comes in. If it is not equal, A0 and B0, because 0 is the index for width, then you just do A0 minus 0, which means basically increasing order of width. Otherwise, B1 minus A1 means decreasing order of height. And after that, like, this problem reduced to 1D LIS, and all we did, we created that new array. So you remember this array, which had these values 3, 4, 5, 7, because now width was not of any significance to me. So here we can just work with this thing. I think I did 3, 4, 7, 5. I don't see where it is, where I reverse sorted. Okay, here, this one. So this is what I have built, and I will run a LIS on this. And for running the LIS, the exact code I have used was the previous code. Solve this problem. Okay, and then we will go to the last problem. I think we have 15 minutes, so we may have to spend a little bit more time, but this is also a very good problem. So let's look at it. Super egg drop. So let me drink water and then I will explain you the problem. You can read it if you want. Okay, so the problem is, let me put it here. Okay, let me make a space on table also. I don't have any example. I don't have any examples. So I will have to refer to lead code example if required. But the problem is pretty clear that you are given like, a building, you can drop, eggs from all these floors. And the thing is that maybe after certain floor, let's call it floor F, what will happen if you drop an egg, it will break. Egg will break after certain floor. So if it did break at F, then it will definitely break at F plus 1, F plus 2, and like that it will continue to go on. And also you are given certain number of eggs. K could be any constant, 1, 2, 3, I don't know, but these are number of eggs. And what we have to find is minimum number of egg drop. So we have to find min number of drops to find with certainty. And that if you drop an egg and you are given these values, then egg will break. So we have to find that number of drops. So whatever could be your worst case, you have to be prepared for that. Okay. So we have been given n floors, kx. So think like, suppose you were given just one egg. So in that case, I cannot take any risk actually. I cannot start dropping from some arbitrary floor because then I cannot determine it. So if I have just one egg, then I have to go drop from here, drop from here, drop from here. Suppose if it breaks on third floor, then I can tell, hey, third is the floor and that is your answer. But if it doesn't break, I have to continue doing that. So in worst case, I have to go to all the floors if I have just one egg, right? Suppose you had three floors. So you will go on first, second, and third, and you will drop egg and you can find it. Suppose you have 2 eggs, for example. Will it take me still 2 drops or less drops, by the way? Having extra egg, does it help me or not?
I think it does.
It
You
does,
still
right?
need to drop, right? Because let's say if you go with one floor drop, you don't know that drop at that floor or maybe drop some floor under that.
Sorry, can you repeat, Leon, what you said?
I'm saying you still need an extra egg. It doesn't help.
So you are saying having 2 eggs doesn't help?
Yeah.
So suppose I had 2 eggs, then I think I can take some risk. The risk I can take, maybe suppose I tried directly this floor. Okay. I have 2 eggs. So 1 egg is not used so far, and 1 egg I did use it. So there could be 2 cases. Suppose it breaks, right, on second floor itself. Then I can use my reserved egg directly here. I can come and I can answer. If it breaks or doesn't break, I can answer my thing in 2 query, like in 2 drops, for example. Suppose if it did not break, right? If it didn't break, then I can reuse the same egg to come here on the 3rd floor, and then I can determine it, because it can either break or not break. If it breaks, then in 2 drops, we are anyway able to find it, right? So everything is possible in 2 drops if I have 2 eggs. If I had just 1 egg, then I have to go and drop on the lowermost floor, then the next floor, then the next floor, and so on. That is at least one strategy. Does that make sense, Leon?
Yeah, I'm saying if we have only 3 floor and if we have extra egg, it doesn't. It's not helping because we always can go from the first one, right? If it drop and we know that, then we go to the second one. The second floor, if the second floor not drop, we know the 3rd floor it have to break it.
Right, but the question is, that is why the question is this one. You are optimizing on this minimum number of drops.
You can find within 2 drops, because in this particular case, number of eggs plus 1 is equal to number of floors. But I don't know if there was like 15 floors and you have 2 eggs, how would you determine with 2 drops?
So there are 2 things. Okay. So I can give you a brief idea. I will not give you the exact answer. Of course, we will figure that out. But why it is better, that part is very clear. Suppose you had 15 floor, right? Suppose you had 15 floor. I have 2 eggs. I can go and drop from maybe 7th floor, 8th floor, right? My first egg. Suppose it breaks. If it breaks, then I can 1 by 1 go with my 1 egg, like 1, 1, 1. So in 8 or 9, depending on what I chose, 9 drops, I can figure that out. If it didn't break, then I can go here and I can start dropping from here. And then in that case, I have still 2 eggs left. So maybe I can find even a better answer. But I can tell you that I can figure things out in 8 or 9 for sure. But if I have just 1 egg, then I have to go like this. I cannot take any risk, because then if I take risk, then I cannot answer the query. Does that explain why it is better to have more eggs?
Yeah, I'm just saying, like, yeah, if you choose 8 and if it breaks, then you need at least 9 drops. So yeah.
Right. So the point is, to minimize number of drops, having extra egg is always useful, right? That we now agree with these examples, right?
Right.
So, and our question is to minimize number of drops, okay? So now, as usual, what we will do, we will try to generalize it. And we also have less time, so that is why also we'll try to generalize it. So here, instead of thinking all those things, let's think in an abstract way. Suppose this was the ith floor. And suppose you had n eggs and k egg, sorry, n floors total and k eggs to begin with. Let me call it f and k is the answer for this problem, which we just, talked about, minimum number of drops. So there are only two cases. First case is maybe the egg breaks, maybe. So if the egg breaks, then I wasted one effort to test this out, testing out. So what is my effort here? If it breaks, then now I have this subproblem, right? Smaller subproblem. It has to be less than I-1. Actually, I-1 floor is left there. So my question is now reduced to, hey, now you only have to worry about I-1 floors. And then also your egg did break. So now you are left with k plus 1 eggs, right? Other case, if it didn't break, then I have to figure out this part, right? So this height was I-1 left. Here it will be n minus I, right? So my question would be, actually, let me put it like this. Second case, egg didn't break. So I still have, actually, no, I still have, that is the second parameter, n minus I floor to figure out if kx left, right? Is that the right recurrence for this?
Right. Yes.
Okay, so
Minimum
now
of
it
that,
is a
right?
small problem.
Minimum
if
of the
it-
two, right?
Sorry?
Isn't it the minimum of the two?
Oh yeah. So it's like actually not minimum, sorry. It's max of 2 because we have to be careful about the worst case, right?
Right.
Because you don't know how it will happen. So you have to give answer with certainty. That's why this word was also used. Whenever we are doing something, we have to always think about worst case. So suppose this value was 10 and this value was 4, then you will say, hey, in worst case 11, in 11 drop, I will figure out if you give me these many eggs, doesn't matter what happens, what kind of, because we don't control that part, that whether egg will break or not. So 1 plus max of these things will give us this value. And then now it is a kind of DP problem where we have now smaller subproblems. And now also we have some base case that if you have only one egg, you have to go and check each floor one by one, right?
Like the second equation, recursion equation, we don't break the egg, right? So we still have the k egg.
Yes, you still have the k eggs.
Okay.
That's why k egg is still there.
And can we divide the array in such a way that maybe it can be optimized better, right? Not just a binary.
Oh yeah.
If we still have k egg, we have more chances.
Right. So yeah, this problem has been studied by mathematicians and there are multiple solutions for this. So whatever solution I am proposing, it has even a better solution. So if you go to brilliant.org and search for egg drop problem, they have done all kind of analysis and there is a mathematical answer also. And very, you can read that. But I didn't actually read all of those. So I will continue with our basic DP solution, okay?
Yes.
Okay, so this is fine. The base case is pretty evident. If you have just one egg, then of course you have to try n times with one egg. The other thing could be if a floor is 0, floor is 0, then that would be another one. Okay, you don't need any try, maybe that would be 0. So that is base case, and then we have to just solve this, and then we can go and try each value of I one by one, right? I can be 1, I can be 2, I can be 3, and like that. And then that will give you a DP solution. And that is one of the solution for sure.
So you're gonna select the ith floor using binary search, right?
More interesting part of this. So actual binary search will come, and how would I do that? So let's see. And I will show you the code in the end, and then we will see how part, but let's try to understand why binary search is even possible and how it will work. So my question is, if I increase number of floors, would I need more drops or not?
Yeah.
Number of floor increases, then because I have defined it that, okay, what is the number of drops here? If you look here, minimum number of drops. So if I continue to increase floor size, this function will increase, right? If n increases. And that means if floor number decreases, then that function decreases. Okay. Now we have two functions. One is f I minus 1, k minus 1. Another function is f n minus I, k. You know, I was trying earlier when I was trying brute force DP, I was using all values from first floor, second floor, third floor, maybe I was iterating over all these floors, and I was doing the calculation. But can I say that while I'm doing this, this fi minus 1, this function is an increasing function because I is increasing, right? For the fixed value of k,
Right.
because k is constant here in both the cases. And as I increases, this value is decreasing also. So number of floor is decreasing. So this is a monotonically increasing function, and this is a monotonically decreasing function, right? So if I try to draw it here, it can have something like this nature. So one of the function is increasing. So let me try to put it like this, though it will not be a straight line, but idea remains something like this. Okay. This one is your that function f n minus I k function. Let's call this guy. And this one is f, what was that? I minus 1. Yeah, f I minus 1, k minus 1. What is that function? Okay. Our answer is, if you see, our answer is 1 plus max of these two values. So suppose I can have any value. Suppose this is our I value, 0, 1, 2, up to, I don't know, n minus 1 or n. Suppose I am looking at here. So let's look at here. What would be the answer? Whatever is the max. Whatever is the max here means this value is the max here, right? Then, and I will add 1 to it because that was my function, whatever is the max. And then if I look at here, then my value is this guy, right? If I reach here, then my value is this guy. If I reach here, my value is this guy. I'm not going down because I have to always take the max in both the cases. I wish I could use another color, but today that's not feasible. So let's using these dots. So now your selection choice is happening like this, guys. Like this, it's going like this. So where the minimum will occur in this function? This point, right?
Yeah, when both are equal.
When both are equal or both are intersecting. That is your search space. That is the ideal place to search. So now if I have that clear, I can get the result from both the parts. I can ask, hey, you always give me value for left. This is my left function. You always give me value for right. Okay. And suppose randomly I started with this value. Okay, this was one possible value. So let me binary search it. I will have low here, I will have high here. Suppose this was mid for some reason. So if I can see that right is greater than left, in this case actually left is greater than right, because see this function, this function is left, right? This function is left. So if left is greater than right, what does that mean? That we are in this area. If it is the other way, then I am in this area, right? So I can move my then mid, then I would say, hey, actually come towards left side. So I will move my high here in this direction. If this guy is bigger, then I will say, hey, come this side. And eventually there will be a place where they will meet, or they will be very close, right? Maybe it does not have integral solution, right? So maybe they are adjacent to each other, and I can compare both, and I will take the best, and then I'm done. So that is the improvement on the previous approach, like optimizing the DP, where now instead of checking all values of I, all these values of I, we are binary searching. We are just taking any arbitrary mid and we are sifting it. We are sifting till we have a very close value for left and right part. And then that would give me the ideal solution. So this search is optimized. Is the idea clear? Then I will show the code and then it will be even more clear.
So where you get the mid, let's say you have low and high.
Yeah.
If you get the mid, wouldn't that go directly to the lowest one, right?
No. So you cannot assume that this function is like the way I did draw. It could be a different kind of drawing. You also don't know the value of it. So it could have a one function is maybe going like this. One function is increasing at this pace, right?
Okay.
In that case, you can have your value here, but also maybe this value is not integer point, but drop has to be an integer value, right? I cannot say I did 2.5 drop or 2.33 drop, right? So I will try to get as close to this as possible. There will be a point where low and high will stop, and then I will choose the best value out of them, even if they don't match, to give me the best answer.
Why do you say there won't be an integral solution? Because you're always dropping from a floor and you will know whether they dropped or not, or broke or not.
That is fine. What would be the not? So these functions can match at any value, right? We don't know the function. We are looking at these functions. It is not denoting the number of drops. It is giving us some value, right? And then these equations, they can intersect at some point of time, right? Suppose I write an equation of line. I can always write an equation of line which is increasing and decreasing in an order, whether they are not meeting at the integer point, right?
But currently those functions are constrained by n and k. So what I'm proposing is they will meet at some point, and that will give you an integer value, and that would be the minimum point where you can safely say. Why you're saying that it may not meet is what I didn't get that one. Because here those functions are constrained by n and k. It's not a random function.
Okay, that is fine. It is giving you number of drops, right?
Yeah.
Yeah. So what I am saying, and I don't know, we have to actually put printout to derive that maybe one value tells me, okay, you need 98 drops to figure things out. Another one is telling me you need just 97 drops, right? Then I would say, okay, and then my, these low and high pointers, they are adjacent to each other, and now they cannot move any further. Then I would say, hey, who gave you the best value? Then just choose that value. I'm talking in a general sense, but if it just matches here, then well, that is pretty good actually. Then I can do early return even.
Yeah, that makes sense.
Yeah. But the idea is clear, right? How we can apply things are working, how we optimize on top of it. So with that, let me show the code, and that will explain, and that is the last part of this session. I think we are still not bad on time. So okay. So as we talked about, this is your function f, and then this was the base case. If n is less than equal to 1 or just 1k, we just return n. This is the memoization part, where if it is already calculated, we are done with it. Otherwise, we have this 2 pointers, low, high, and then I will continue to update my result. If whenever I see a better result, I will try to take the minimum of it so that I can finally return it. And then I'm doing this thing. Okay, instead of going one by one, try to check this mid thing. Okay, and then now we provide this mid value to our helper function. So this is the first case where this function was increasing, right? Because mid was our I value. So this is an increasing function. That was the left part. And another one was the right part, which was the decreasing function in this picture, right? So here is the increasing function. If you can see my cursor, and then value I get, I continue to update my best result so far. I use +1 also. And then I move my low and high depending on the criteria we talked about. If right is greater than left, then low moves, as you can see with this. If right is greater than left, then low has to move. And that was this picture, this part. If we are in this area, then low has to come this side. Otherwise, high has to come here. And then after we are done.
One more question.
Yeah.
You said that we have to say for certainty. So why is the result the minimum of the two? Shouldn't be the maximum? Like if you say that there is 97 drops and 96 drops, for certainty, won't you say?
Yeah. I am still taking max, right?
Yeah. But
yeah, go ahead.
Yeah, the result is min. That's why I asked. The max part I got, max of left comma right +1. That part I got. I didn't understand why you're taking the minimum of that value and the result.
Yeah, I will explain you. So this part is clear, right? So I took, suppose I choose some mid value, and then I calculated something. So maybe I was here. In my case, my mid was here. As in this picture, it will be clear. This was my mid area, okay? So my answer is here, plus 1. Suppose this was 108. So I will update my value. Hey, I have found something 109. But it also tells, hey, actually right is greater than left. If you try to go towards this side, maybe you will find a better answer. So now you start to get 105. So you will say, okay, I have a better answer. I have one more value. And doing this,
Okay, got mine.
this thing, you reach here. Okay.
Yeah. Now it became the diagram made it clear. Thank you.
No problem. So I think that was the idea. And then that's it, guys. I think we finished the session. At least that was what I was planning to cover today. Hopefully you guys enjoyed it.
Yeah, that's great.
Okay.
Yeah, this was great. Thank you.
Yeah, thank
It
you.
was super actually. Yeah, but the last one is slightly not
Ask me.
so easy to follow, right? Yeah.
No, you can ask me. It's a best time to ask. I will forget myself. So please ask if you have another question.
No, not the question, but the way the implementation is.
Yeah.
Not so easy to come up with, but yeah.
Oh, yeah. Idea was, see, DP has certain optimization techniques, right? If you think the previous problem we were doing LIS, right? That was also a DP problem, right? When we started with this example.
Mm-hmm.
And then we, or someone, not we, someone thought about idea how to, rather than going one by one, because we are searching something, right? So when we are extensively searching one by one, there are a couple of ways only to how the search could be faster. Sometimes when the search space is used and there is some greedy aspect of it, you can ignore a lot of things, right?
Mm-hmm.
That is one idea. Another idea is if there could be something like function, you know anything about the function, then you can ignore a lot of values. So that is what happened in this few problems. And guys, it's, if somebody did research on this problem, like, you know, there are mathematical papers on it, then you should not feel bad about not, like, you know, thinking it yourself. I mean, maybe, like, you know, this idea will help to solve many other problems in future.
Mm-hmm.
So
Yeah, the LS part is more clear. Yeah, absolutely. But the super egg draw gap, yeah, there are some gray areas. Absolutely, yeah.
yeah, but is the explanation clear for
Yeah,
this
yeah.
particular problem?
At
Okay.
least, yeah, in this scope, perfect. Yeah.
Right. So what I learned, like, you know, what I would like you guys also, maybe you have your other strategy to learn, that when we had, like, you know, two different functions, one had this, you know, going down, going up, and then we had to find the minimum, right? It may happen in some other problem also. It's a very common problem, right?
Mm-hmm.
It may not have been in only this particular problem. So the thing to take out of it is why and how we did this. If we are able to, like, you know, apply this learning to other problems, then it's a very good exercise, right?
Mm-hmm. Yeah.
Yeah. So that will help. And then I think we can, you know, if anyone has any final question, feel free to ask.
Roger, one thing I might have skipped this. So why are we moving towards this point of commonality, where both of them are either equal or close to each other?
Okay, why we are moving towards each other? Because see, we want to find, our function is telling that you have two values. Okay.
Okay.
One function, this was one case. Okay, this was one case, and this was other case. And you have to find.
Assuming, yeah. So is it possible that these functions do not overlap?
No, it's not possible that they won't overlap.
Okay.
Or they may at least touch. Suppose, like, you know, Because see, one guy is definitely increasing, one guy is definitely increasing, and the search space is same. Like, they are constrained to be in this area. So it is possible that they don't move. So maybe your drawing could be like, only one guy moves. It could be like, hey, actually this is the case. You have these two, you select whatever works for you. So you have to select this guy in that case, like, because it never came down, then you will still have to take the max value, right? So that is possible. So in that case, what will happen? Your high will continue to remain here and your low will continue to make progress this way, this way, this way, this way. And why? I know whenever they intersect, I will get the least value. That's why we were trying to move. So we are still, making progress. See, these two lines are not parallel to each other, right?
Yeah.
One guy is decreasing, one guy is increasing. So they are building a funnel. So eventually somewhere they will try to meet. Maybe they don't exactly meet, but still you will find the best position where you can take the value, and then that would be your best value.
Yeah.
Yeah, that's great.
Okay, guys. So any other question on this problem, or we can otherwise stop the share. And then if you guys have time, we can talk. Or yeah, but that was the last part. Feel free to reach out to me if you have any question. I think you should have access to this doc. If not, you can find it on somewhere on our Discord server.
Yeah, sure.
Okay, cool. So let me stop share this point of time.